So first of all, thanks Matthew for the introduction. And my name is Kai Jansen. I'm a PhD student at the Ruhr University in Bochum, Germany. And today I'm going to present CrowdGPS-Sec, a system to detect and localize GPS spoofing attacks by using a crowdsourcing sensor network and picking up aircraft broadcast signals. This is joint work with my colleagues Matthias Schäfer and Jens Schmidt from TU Kaiserslautern, Daniel Moser from ETH Zurich, Vincent Lenders from Amerswiss, and Christina Pepper from NYU Abu Dhabi. In June last year, the US Department of Transportation issued a warning of GPS interference in the Black Sea. So one might wonder what has happened. Ships that were cruising in the vicinity of the Russian border in the Black Sea actually reported their position not at a sea level indicated by the orange dot here, but however they reported a GPS position that was close to the runways of a nearby airport. And actually, to get this clear, this was one of the first publicly known events of GPS spoofing, where an unknown remote attacker successfully performed GPS spoofing on multiple victims over an extended period of time. Later that year, GPS World, an online news platform for navigation use, tried to reason a little bit about the spoofer location, and they came up with this broader map where they indicated possible locations. They based their analysis on received signal strength or the elevation of the underlying terrain. And however, as you can see here, the proliferation of their indicated area is around tens of kilometers wide. The question that this talk is going to answer is whether we can do it better, and if we can do so, by how much can we do it better? So by how much can we localize a GPS spoofing source? First of all, let me briefly introduce the databases we are using nowadays. Aircraft use additional systems and protocol to ease air traffic surveillance. So for example, they broadcast ADS-B or FLAM signals, which in turn contain status reports that are made up by at least an identification, data or GPS data on the position, and additional data on their movement. To pick up these signals, you could use ground-based sensors, and this can be as easy as a Raspberry Pi coupled with a tiny RTL dongle and a very simple antenna. A network that already performs so is the Open Sky network, and two of my co-authors were actually members of the founding team. And as you can see here, if multiple of those sensors, and that particular network is made up of around or more than 700 voluntarily operated sensors. If they unite their data, you can actually generate those live air traffic maps. This forms the databases we use. So we now have a look at our threat model. We consider a GPS spoofing attacker. 10 years ago, you needed a special purpose device, which was coupled with a high cost, high complexity in order to perform such attacks. However, with the years, the costs went down, the complexity went down, and nowadays you are able to build your own GPS spoofing attacker by using a software-defined radio running software that is freely available on the internet. So what happens now if such an attacker tries to target aircraft? It will broadcast its signal toward the air, and in the case of a successful attack, the aircraft will use those fake positions and broadcast them or rebroadcast them back within their status reports down to the Earth, where they are now picked up by the sensors of the network. We designed CrowdGPS-Sec to answer two questions. So the first question is, how can we detect such an ongoing spoofing attack? And the second question is, in the case we were able to detect a spoofing attack, can we actually localize the spoofing source? First of all, since you have just seen that aircraft can actually lie about their own position in case of spoofing, we implemented a second source of positioning, of aircraft positioning, by implementing a multilateration approach based on time difference of arrival. So this picture briefly depicts the situation here. An aircraft broadcasts a signal, which is then received by multiple sensors on ground. And depending on the differences in the arrival times and the differences between the aircraft and the sensors, we can actually relate both of these parts of the equation. And possible solutions are marked here with a blue line, where the source could have been. And if we extend those systems further, so for example using 3 sensors or even more, we get more of these equations, which then ultimately intersect in a distinct point, which marks the most likely position of the aircraft. Having built a secondary source of aircraft localization, we are now ready to have a look at how we can detect spoofing attacks. We designed 2 tests for that. So the first test is based on a comparison between our position that we just calculated from the multilateration approach with the position of that the aircraft broadcasts itself. So if the inconsistencies between both positions are too high, this could be a first indication of a spoofing attack. The second test is a mutual comparison between the ADS-B positions of different aircrafts. So under normal operation, aircraft positions won't be the same. However, considering a spoofing attack, these can actually be overlapping, which can then in turn point towards a possible spoofing incident. Having answered the first question, so we are now able to detect spoofing attacks. The question that still remains unanswered is how can we now localize a spoofing source? Let's take a step back and have a look at the GPS spoofer again. In case that the GPS spoofer targets aircraft, it will be likely that the spoofer decides to spoof a certain track of a certain speed with the purpose of manipulating a certain aircraft track. And when the signal is sent out and received by different aircraft at different distances to the spoofing source, they will consequently report different positions on the spoofed track. So for example, if aircraft 1 here receives the signal a little bit earlier than aircraft 2, it will report a position that is a little bit ahead on track as compared to aircraft 2, which will report a position that is a little bit behind on track. And we can now calculate the differences on this spoofed track. And this is the difference between their reported ADS-B positions. Let's generalize this scenario again. If we have a spoofer now that sends out a signal that is received by 2 aircraft, we can now build relations between the differences in their physical locations and our calculated differences in the ADS-B reports. And if we relate both of these values, we can again obtain multiple solutions, which is marked by this blue line here. And if we extend the system by using 3 aircraft or multiple aircraft, we obtain multiple of those equations, and all of the solutions of the equations will now intersect hopefully in a single point, which now indicates the spoofing source. From a theoretical point of view, this completes our system. We are now able to first detect spoofing attacks, and second, try to reason about the spoofer location. However, since we are dealing with measurements and also over the wireless channel, we need to have a proper error assessment. If we have a closer look at our relations here, we identified 3 distinct parameters that have a certain impact on our localization performance. So first of all, there's the noise or the error in our MLAT system. We analyzed it to have a very low impact on the spoofer localization accuracy. On the other hand, the error in the GPS noise in the ADSB positions, or in the differences in the ADSB positions were analyzed to have a very high impact on the localization performance. And lastly, the spoofed track velocity has also an impact on our achieved accuracy. However, we analyzed it to have only a moderate impact. To get a little bit more into detail here, I have a closer look at the GPS noise, or the impact of the GPS noise. We simulated a spoofing attack and sampled real-world data from the Open Sky network and performed several simulations and assumed different values for the GPS noise. So we made simulations with more conservative error models and went down to a little bit beneficial models. Using conservative models, we actually achieved a spoofer localization with an offset of just 8.4 kilometers. However, if we consider more beneficial error models, we can actually bring down this accuracy down to an error of only a few meters. If we take a look back at our initial slide of the broad localization that the GPS world performed, and if we visualize now our results, we actually can shrink this area to just a very, very small area here. And I have to say, this is not the real location. This is just a visualization. Let me finally make two major remarks of our system. We were able to achieve all of this with just the data that sensors provided that were actually not the target of the spoofer, but only relayed aircraft broadcast signals. And finally, our system neither requires any changes in the protocols nor the hardware, and is actually ready to be implemented. It only uses an existing infrastructure. Let's come to a conclusion. I've showed you two different tests of how to detect GPS spoofing. First of all, we compared MLOT positions with ADSB positions. And the second test was mutual comparison between different ADSB positions. I've showed how our spoofing localization performs, and by comparing distances between the spoofing source and aircraft with the distances in the reported ADSB positions. And finally, I visualized our achievable localization performance. And with that, I want to thank you for your attention, and I want to also thank two of my close colleagues, Katharina and David, for helping out with my slides.
Remember, please state your name and affiliation.
Hi, Karen Utek, MIT Lincoln Labs. I was curious, it's crowdsourced. So how affected do you think it would be by some of those sensors in the crowd being malicious?
That's a very, very good question. I think as long as the malicious sensors cannot overvote the beneath sensors, we are fine. Of course, if all of these sensors lie, we don't have any means to detect that.
Hi, Patrick Trainer from Florida. This is really cool work. I was just curious, how much historical data do you have? I'd heard about this incident with the ship, but it would be really interesting if you could go back in time and actually find other similar results that maybe we didn't know about. Am I ruining a future paper? Or?
Yeah. So the Open Sky network actually collects data since several years. However, we tried to also find data on this spoofing event, the Black Sea. However, there were no sensors available that picked up sensors from that specific time. So if you have data from that, feel free to give me.
Thank you.
So I have, I guess, the final question. What range of vehicles does this apply to? Military aircraft, drones, ships also? I know they're spoofing in ships as a kind of vulnerability. Can you give us some insight onto what changes would need to be made, what it applies to?
So our system just requires or the signals to be affected by the GPS spoofing attack. So it doesn't matter if it's drones or vehicles or aircraft. If we get those information from the signals, we are fine with that. So you can also use everything that uses a GPS receiver.
Cool. Let's thank our speaker.